Okay, so we can talk through how we're going to go about solving this problem, and this is basically the same setup as in the relativity of simultaneity problem, except instead of launching two photons from the middle of the train, Alice is launching two baseballs. Now there's a key difference, which is that although the photons do not get a speed boost because of the train's motion in Bob's frame, the baseballs will. Okay, so I've drawn the picture in Alice's frame at the time of launch, and then we can sketch the same scenario after the balls arrive, or the instant the balls arrive. And again, this is in Alice's frame. Bob will have moved, actually. Let me make sure that I put Bob in the right place here. Bob will have moved over and continues to move at minus 21 meters per second. So in Alice's frame, it's very straightforward to see that it's going to take 2 seconds for the balls to reach the wall, right? Because we know the distance traveled is given by the speed times the time elapsed. Okay, so let's call that distance equals the speed times time. In this case, the speed is the velocity of, say, the red ball relative to the train times the time elapsed. So t is equal to d over v red ball relative to train, and that's the 6 meters over the 3 meters per second, gives me 2 seconds, okay? And you can do the same for the blue ball. You're going to find the same result, that it takes 2 seconds for the ball to reach the wall. So they're launched at the same time. It takes 2 seconds for each ball to get there, so the balls arrive at the same time. Now the goal here in parts C and D is to show that the red and the blue ball also take 2 seconds as measured by Bob. So we're going to redraw the picture in Bob's frame, and we're not going to assume that it takes 2 seconds. We're going to show that it takes 2 seconds. And what that means is that at low speeds, we have basically everybody agrees on the time. There's a universal time. But of course, we know that at high speeds, that's no longer true. At high speeds, or speeds that are comparable to the speed of light, the rate that clocks tick and the readings on clocks are frame dependent. Okay, so now let's draw the situation in Bob's frame. So in Bob's frame, we know that the train is moving, and it's moving to the right. So v of train relative to ground is plus 21 meters per second, okay? And v of Bob is 0, because we're in Bob's frame. And let's see, you might be tempted to draw something like this, where we have 3 meters per second for each ball, because we know that the ball is thrown at 3 meters per second. But avoid that temptation, right? Because those are velocities in the train frame, in Alice's frame. This is a drawing in Bob's frame. So we want to draw the velocity of these objects in the frame that we're actually talking about in this moment. So we want the velocity of the red ball relative to the ground. Okay, so we need to calculate that. So we know that v of rg is vr of something plus v of that something relative to g. And what do we know? Well, we know velocities relative to the train, so let's put that in there. We know that the velocity of the red ball relative to the train is 3 meters per second, and we know the train relative to the ground is 3 meters per second. So let's actually write this explicitly out here. We're given VRT is plus 3. We're given that V blue ball relative to the train is minus 3, thrown to the left relative to the train. And we know that the train relative to the ground is plus 21. Okay, so we actually have all the quantities that we need. We know VRT, plus 3, and we know VTG, plus 21. So we can just put that in, plus 3 and plus 21, for a grand total of 24 meters per second. Okay, so now we can draw that here. 24 meters per second is v of the red ball relative to the ground. How about the blue ball? Okay, well, we're going to play the same game. It's v of b, blue ball relative to train, plus v of train relative to ground. But again, we know both of those. vbt now is minus 3, and vtg is still 21. So we have minus 3 meters per second plus 21 meters per second is 18 meters per second. But it's not negative 18, it's positive 18 meters per second. So perhaps surprisingly, the blue ball in Bob's frame, the blue ball has a velocity vector that also points to the right, but it's not quite as long as the red arrow because it's 18 to the right instead of 24 to the right. Okay, so V blue relative to the ground, or relative to Bob, is 18. So this is interesting. So as we prepare to draw our second diagram, we need to make sure that in the next diagram, both the red and the blue balls have moved to the right. Okay, so let's draw that diagram. Oops. Yeah, this is an unfortunate aspect of this program. Let's see here. Bring you over here just as a reference and kind of tuck you away, and then we'll get rid of these guys for now. Okay, and below here we will draw the second diagram. Okay, so Bob hasn't moved because we're in Bob's frame, but the train has moved. Okay, so let's see. How about right here? And this is the instant that the two balls arrive. And the train is still moving at plus 21 meters per second. Okay. Now, in part D, so we've drawn now the diagrams in Bob's frame, and we can just kind of be really clear. We're going to indicate that Bob hasn't moved. So that dash line indicates that Bob is in the same left-right location in both pictures. Okay, we want to calculate the travel time for each ball to reach the wall. All right, let's do this with the blue ball first. So I'll call it the blue travel time. Okay. So we're going to annotate our picture. I'm going to draw a purple dashed line where the ball starts and where the ball ends. Okay. And I'll call that D ball. So we have D ball is the distance that the ball travels. Okay. And we know that that's going to be given by its velocity times the elapsed time. So that's the velocity of the ball, the blue ball, relative to the ground, because we're in the ground frame, multiplied by some time that has gone by between the two pictures. Great. We have some other information in this diagram. We know the length of this train is 12 meters, and so we know half of the length of that train is 6 meters. Okay. And the other thing that we know, which will complete everything that we need, is that the wall has also moved. So I'll call that D wall. Right? Notice that the wall used to be here, and now it's here, and the distance traveled by the wall is given by that interval D wall. Great. But D wall, the wall is an object that has a velocity and is traveling for amount of time also. And the velocity of the wall is the train's velocity, VTG times T. Okay, so we now have an expression for the distance the wall traveled, in terms of time elapsed, and then we also have the 6 meters. Now here's where drawing a good picture is so important. If you look at the picture tells you the equation, right? And the equation is that if I add up these two small pieces, I have to get the big piece, right? So in words, I can say that the distance the wall travels is equal to the sum of 6 meters and the distance that the ball travels. Okay, so let's just write that out. We have d wall equals 6 meters plus d ball. Right? But we have values for d wall and d ball. D wall is the train velocity times t, and d ball is the ball's velocity times t. Okay, so our goal is to solve for t. So we have vtg times time minus vbg times time is equal to 6 meters. Okay, so we'll continue this up above. VTG is 21 meters per second multiplied by time. VBG is the, we calculated that before. VBG we said was 18 meters per second. We calculated it down in that corner. So we can do minus 18 meters per second multiplied by t is equal to 6 meters. 21 minus 18 is 3. So we have 3 meters per second times t is equal to 6 meters, or t is equal to 2 seconds. Okay, so this is exactly the same number that we found in Alice's frame. So whether you're on the train or standing on the ground, you would agree that it takes 2 seconds for the blue ball to reach the wall. So I'm going to stop there and let you guys repeat this process for the red ball, understanding that the result is still going to be 2 seconds, but I want you to practice doing it. In particular, practice annotating your 2 diagrams to figure out what the equation is going to be on how these 3 quantities relate to each other for the red ball. And then I challenge you to extend the problem with part E. Instead of putting in numbers for the ball speed and the train speed, just leave them as symbols. And the beautiful thing there is when you calculate this time t in terms of these symbols, what you find is that the train speed relative to the ground will cancel out, and the only thing that matters is the velocity of the balls relative to the train. And so it then becomes very clear that no matter what frame of reference you're in, you're going to get the same result because the train speed relative to the ground doesn't even exist in the final answer. All right, well, good luck with that, and we'll see you again soon. Bye-bye.